Malaria is far older than humanity, with evidence of its parasites found in 30-million-year-old amber. Its impact on human civilization has been recorded for millennia. Ancient descriptions of symptoms consistent with malaria, such as debilitating periodic fevers, chills, and an enlarged spleen, are found in texts from around the world. These include Chinese medical texts, c. 2700 BC, Indian Vedic scriptures, c. 1500 BC, and Egyptian papyri, c. 1550 BC. The Greek physician Hippocrates, c. 400 BC, provided detailed descriptions of these fevers, classifying them as tertian, every third day, and quartan, every fourth day, which perfectly match the fever cycles of different malaria parasite species. For centuries, the cause of the disease was a mystery. Because it was most common in marshy, swampy areas, the prevailing theory was that it was caused by miasma, or toxic vapors rising from the fetid water. This belief is the direct origin of the disease's name. In medieval Italian, it was called malaria, meaning bad air. Long before scientists understood what caused malaria, a partial cure was found in the bark of a South American tree. Indigenous peoples of Peru had long used the bark of the cinchona tree to treat fevers. In the 1630s, Jesuit missionaries learned of the bark's properties and introduced it to Europe, where it became known as Jesuit's bark. In 1820, French chemists Pierre-Joseph Pelletier and Joseph Bename Caventou successfully isolated the bark's active alkaloid ingredient, quinine. This became the world's first effective anti-malarial drug and remained the primary treatment for over 300 years. The scientific breakthroughs, late 19th century, revolutionized the understanding of malaria, definitively shifting the blame from bad air to a microscopic culprit and its insect carrier. Discovery of the parasite. In 1880, a French army surgeon named Charles-Louis Alphonse Lauverin, while working in Algeria, made a groundbreaking observation. Using a microscope to examine the blood of a soldier suffering from a malarial fever, he saw moving, pigmented, spherical bodies inside the red blood cells. He realized he was looking at a living microorganism, a protozoan parasite. This was the first time a protozoan was identified as the cause of a human disease. For this discovery, he was awarded the Nobel Prize in 1907. Discovery of the transmission. Lauverin had found the what, but the how was still unknown. Sir Ronald Ross, a British medical officer in India, was convinced that mosquitoes were the vector. In 1897, he proved that mosquitoes could transmit the parasite in birds, identifying the parasite developing within the gastrointestinal tract of mosquitoes that had fed on infected birds. This proved the mosquito transmission link and won him the Nobel Prize in 1902. An Italian scientist named Gabbani Battista Grassi completed the puzzle. In 1898, he and his team demonstrated that human malaria was specifically transmitted by female Anopheles mosquitoes. With these discoveries, the full picture emerged. The Plasmodium parasite, the agent, was transmitted between humans by the Anopheles, the vector. The 20th century, ambition, and setbacks. Armed with knowledge of the cause and transmission, the 20th century saw the first global, organized efforts to control and eliminate the disease. New drugs and insecticides. During the 1930s and 1940s, synthetic antimalarials were developed, most notably chloroquine. It was cheap, safe, and highly effective, and it became the standard treatment for decades. At the same time, the insecticide DDT, dichlorodipenyl trichloroethane, was discovered to be incredibly effective at killing mosquitoes and was used widely to protect troops during World War II. The Global Malaria Eradication Program. In 1955, the World Health Organization launched the ambitious Global Malaria Eradication Program, GMEP. The strategy involved attacking the vector with indoor residual spraying, IRS, using DDT and treating the host with chloroquine. The campaign was spectacularly successful in many regions, eliminating malaria from Europe, North America, and large parts of the Caribbean. The Great Resurgence. The GMPE ultimately failed in its goal of global eradication, particularly in sub-Saharan Africa. By the late 1960s, the campaign collapsed due to two major problems. 1. Drug resistance. The Plasmodium parasite began to evolve resistance to chloroquine, rendering the go-to drug useless. 2. Insecticide resistance. Anopheles mosquitoes evolved resistance to DDT, making spraying ineffective. Furthermore, the program faced financial issues and environmental concerns about DDT's impact on wildlife led to its ban in many countries. Malaria came roaring back, often to pre-eradication levels. A new hope, the discovery of artemisinin. By the 1970s, with chloroquine failing, the world was in desperate need of a new anti-malarial. The breakthrough came from a secret Chinese military research program, Project 523. A scientist on the project, Tu Yu, screened traditional Chinese medicines and focused on sweet wormwood, Artemisia annua, which had been mentioned in a 4th century text for treating fevers. Using a low-temperature extraction method, her team isolated a new, potent anti-malarial compound, artemisinin. This discovery was a game-changer. Today, the standard of care worldwide is artemisinin-based combination therapy, ACT, which pairs artemisinin with a longer-lasting partner drug to slow the development of resistance. For her discovery, Tu Yu was co-awarded the Nobel Prize in 2015. The 21st century, the ongoing fight. Today, the fight against malaria is one of control and regional elimination, with a renewed long-term goal of eventual eradication. The burden remains immense, with over 90% of cases and deaths occurring in sub-Saharan Africa. Modern control tools. The current strategy is a multi-pronged attack. Insecticide-treated nets, ITNs, long-lasting nets hung over beds to create a protective barrier that kills mosquitoes on contact. Indoor residual spraying, IRS, still used in targeted areas with a rotation of different insecticides to manage resistance. Diagnostics and treatment. Rapid diagnostic tests, RDTs, allow for quick diagnosis, and ACTs remain the frontline treatment. New challenges. The battle is far from over. The two biggest threats today are parasites showing partial resistance to artemisinin, first seen in Southeast Asia and now detected in Africa, and mosquitoes continuously evolving resistance to the insecticides used in nets and sprays. The dawn of vaccines. For the first time in history, vaccines are part of the malaria toolkit. In 2021, the WHO recommended the widespread use of the RTS, mosquirix, vaccine for children in high-burden areas. It is the first ever approved vaccine for a parasitic disease. In 2023, a second, more effective and cheaper to produce vaccine, 21/Matrix M, was also recommended. The rollout of these vaccines marks a new era in malaria prevention.